Let's finish up RACE-2 of the Secureum Bootcamp with the last question, number 8. And here it says that the in-Secureum DAO will not be susceptible to something like the 2016 DAO Exploit. So what is this about? So we have a contract here in this race, which is a decentralized autonomous organization. And this DAO in 2016 was one of the first contracts that implemented such a decentralized autonomous organization. And unfortunately, it was hacked, and this hack was quite devastating because lots of people had funds in it, lots of people invested into this DAO, and unfortunately it ended up getting hacked. And it was in fact so devastating that the community decided to hard fork Ethereum to undo the exploit, to make it as if it had never happened. And this kind of goes against blockchain philosophy, because the whole point of blockchain is that you have a chain of blocks and you cannot change any of the contents of these blocks, because then the entire chain would be invalid, because the hashes would no longer work out, basically. That's the entire point of a blockchain. And they kind of broke this promise that the blockchain gives by hard forking the Ethereum and, well, undoing this hack from ever having happened, because it was just so devastating. So many funds had been lost that they decided that it was worth doing that. And, well, was it the right decision? It's arguable. At the end of the day, the market decided to go along with it, because the other side of the fork, which was Ethereum Classic, wasn't really successful. So in terms of the market, it seems to have been the right decision, but it is still used as one of the biggest arguments to say that Ethereum is not really decentralized, that there's too many people who have too much power in Ethereum, and all those critiques that are still today levied against Ethereum are often based on this hack. Whether that's fair or not, I will not argue here. But getting back to the actual question at hand here, what was the DAO exploit? The DAO exploit was one of the, if not the first occurrences of an exploit of reentrancy. It wasn't as if reentrancy was not a known problem. People certainly knew about it. As far as I've heard, the DAO actually had a reentrancy problem before the exploit, and they fixed it. So they were aware of this matter, of this vector, basically. But I think they called it differently back then. It wasn't called reentrancy at that point, but that doesn't really matter. But unfortunately, they overlooked in one function, which was called, I think, the split DAO function, which allowed members to split off from the main DAO into their own DAO. And while splitting off, because basically this DAO allowed you, like a vault, you could put in Ether and you get a share, basically. And this share represents your share of Ether within this DAO contract. And the problem was that this share, the actual Ether, was sent to this new DAO contract before the shares were invalidated. So before the shares of the share amounts of this Ether in the DAO were reset to 0, so that after moving away the funds, that the share had been voided, basically, and now are shares of a different DAO. This wasn't done in the right order, because what it did first was sending out the Ether and therefore giving control over the execution to this new DAO. And then this new DAO could, or this other contract that was called during this transfer, could just re-enter the DAO or the original DAO contract, could just re-enter it and once again split off from the DAO and once again use the same shares as before the shares were reset to 0. So it's a very classical, or it is the classical reentrancy exploit, basically. And this is what this question is referring to. So, and this question asks whether the in-Secureum DAO, so the DAO of this race is not susceptible because it derives from reentrancy guard.sol, which protects all contract functions by default. So if we look at the code, we can see that indeed we have a reentrancy guard sol here included, which comes from the Open Zeppelin contracts package. And we can also see that the in Secureum DAO contract is extending reentrancy guard, and the option basically claims that just by the fact that in Secureum DAO is extending reentrancy guard, just from this, in Secureum DAO is protected from reentrancy, which is not correct because we need to actually set the non-reentrant modifier on the functions that we want to be protected against reentrancy, and therefore A cannot be true. This is not the reason why the in Secureum DAO is not susceptible to the DAO exploit, to the same problem of the DAO exploit. Then we have option B. Only if it does not have a withdraw ether function vulnerable to reentrancy and makes no external calls. So a withdraw ether function, when you withdraw ether, it makes a call, an external call to another contract. It needs to do this as part of this withdrawal process. So yes, a withdrawal ether function certainly can introduce a reentrancy vulnerability, and also other external calls can introduce a reentrancy vulnerability if the state before this call was made was not properly updated. So arguably, yes, if it does neither have a ether withdraw function and it also does not make any external calls, then indeed our in Secureum DAO will not be susceptible to reentrancy like the original DAO was. So B is correct. Then we have C. It is not susceptible because the Ethereum protocol was fixed after the DAO exploit to prevent such exploits. So while the Ethereum protocol indeed forked to reverse the DAO exploit from ever having happened, this doesn't mean that they actually fixed the problem. Unfortunately, in Ethereum, this reentrancy is such a basic thing that it is really hard to fix on protocol level, basically, because you want to re-enter contracts, not for malicious purposes, just to call that function, to ask for some information or stuff like that. So a reentrancy doesn't necessarily have to be malicious, and it's just a way how you can program, basically, and therefore you can't easily fix this issue at a very low level. Then we have option D, which says because the Solidity language was fixed after the DAO exploit to prevent such exploits. Well, they certainly tried to fix it because they introduced the transfer and send functions, which are now, well, not recommended to be used because they send a hard-coded amount of gas together with the call that they do. They intended this to prevent things like the DAO exploit from happening because this very small amount of gas that they send would basically not allow calling over and over back into the contract. It wouldn't allow re-entering back into the contract that sent the ether value. But the problem there is that hard coding gas is not a good idea because future forks of Ethereum, future changes of the opcodes of the EVM can change the gas cost calculations, and it could therefore in future brick contracts that suddenly require more gas than expected. So they certainly tried to fix it, but they didn't actually fix it in the Solidity language. There's other languages like Viper. Viper is a Python-like language, which is also for programming smart contracts for the EVM. And they actually introduced a reentrancy guard that is basically directly native to the language itself. And that too ended up having problems not too long ago. This implementation within the language itself turned out to have issues, and well, that went wrong too. So all the attempts to fix reentrancy in lower levels were not really successful in many ways. So we still have to rely on either people implementing things properly, following the checks, effects, interactions pattern, or just using reentrancy guards where necessary, where people are not sure whether it's necessary or not. When sometimes functions are so complex that it's hard to tell whether the checks, effects, interactions pattern is really followed. So if you're not sure, maybe just use the reentrancy guard just to be sure. And sometimes circumstances just prevent you from using the checks, effects, and actions pattern. So there too, you might just want to make use of this reentrancy guard pattern. So yeah, with that all out of the way, we can say that B is the only correct option here. If it has neither a withdraw ether function nor make any other external calls, it will indeed not be susceptible to reentrancy, which was used to do the DAO exploit in 2016. And that's race number 2.